100 fireflies as seen from the moon. But the James Webb telescope, with its larger aperture and much finer resolution, will be able to see easily 100 times fainter in the amount of time that it takes. So let me, for the sake of time, say only a few words about the supermassive black hole. So many galaxies will, in the center, have a supermassive black hole. The problem with these things is you can't really see them, so you have to derive indirectly that they exist, you know. And they're nasty things, right? They are, yes, there are regions in space where the density of matter is so large that even light cannot escape. So technically, they're black holes, nothing can escape. But they are not circularly symmetric. I'm not trying to eat my lunch here, but it's trying to explain what a supermassive black hole looks like. So they gobble all this gas and dust and stars, which would be like it's not raisins, it's blueberries in this bagel. And then just the moment they fall into the black hole, they get extremely bright, right? I mean, I can't say how bright, extremely bright. You won't see that from here. No, I guess I just blocked out the image. But the black hole accretion disk, all that stuff that's falling in, is not visible to you because it's surrounding by this dusty torus, which is my bagel. But if I shine it in your direction, it gets annoyingly bright. And I want you to take this in. Yeah? I know it ruins your vision a bit. I want you to take this in. The size of the region where this happens, the supermassive black hole, sucking up this material, is no bigger than the solar system, about Pluto's orbit. But the amount of energy that's being created by this enormously bright accretion disk outshines about 100 trillion suns, or about 1,000 galaxies worth of luminosity. So let that sink in. More than a trillion suns worth of luminosity inside Pluto's orbit. Last time I counted, inside our own Pluto's orbit, it's not a planet anymore, but fine, a dwarf planet. There's only one star, right? That's the sun. Inside this thing, there's 10 to the 14 suns. Now, that's a good place to get a suntan. So we call it a quasar, by the way, when it shines in your face. And here's what it looks like when it doesn't shine in your face. This would be the radio galaxy. This is the Centaurus A galaxy. Many of the respected amateur astronomers will have seen this if they've gone down south. You can see it sort of from lower states in the southern hemisphere. Beautiful spiral that collapsed once upon a time and formed this sort of elliptical dusty disk, a lot of gas and dust, some hot stars still forming. Somewhere dug down deep in the center of all this gas and dust, I call it my Baskins and Robbins galaxy. It has all 31 flavors of color. Somewhere deep inside is the supermassive black hole. And if I had churned this galaxy not just like this, where you could see nothing, but like this, it would look like a quasar. So here's an example of what the galaxy would look like if I turned it the other way at, in this case, a rather high distance or redshift. Redshift 6 with the universe was 7 times smaller than it was today, and roughly a little bit less than that, less old, about 14 times younger than it is today. In 2 infrared colors, 1.2 and 1.6 microns, you can see here's the quasar itself. So this is now not the laser pointer, I won't shine it in your face, but the ultra bright accretion disk around the supermassive black hole shining in your face. And here's a model of a star that we also observed with Hubble in the same way as Mr. Hornbeck is doing it for his dissertation. And here's the difference between the two. There's almost no flux left. We're trying to find the surrounding galaxy. This is a little bit like the chicken and egg problem. There is no galaxy detected in this case. And this is one of the 12 brightest quasars at the largest possible distance in the entire sky. So it's one of the 12 most luminous objects in the universe. And it ain't have no galaxy. So on the scale of chicken and egg, what formed first, the supermassive black hole or the galaxy? It was definitely the egg. The supermassive black hole was there before the chicken. And so somehow the supermassive black hole got there in the center. It's about 1 billion solar masses that has been measured from other data, such as carbon dioxide measurements with radio telescopes. And we know that thing exists. There's a few others here. They look a little technical, but I'll get to the point. Here's again the observation made by Hubble at the 2 wavelengths. Here's the best fit model we can make of the data by very carefully measuring if Hubble is standing still. Of course, it goes around the Earth at the annoying 15 times a day, so it's actually rather unstable temperature-wise. It goes between room temperature and minus 100 degrees centigrade every 48 minutes. So you need to very carefully calibrate the size of the central point. And when you subtract that, you're left over with these 2 smudges. Here's the actual data, and here's the model. And there are 2 galaxies that are falling into a 3rd galaxy that hosts a black hole. And that galaxy is so dusty you can't actually see its surroundings. So it's a small group of galaxies that's forming around this very high redshift quasar in the first billion years. Why is this so important? Well, this whole system is rather bright, much brighter than it should be, about 6 times brighter than a typical galaxy, even in the first billion years. So we call it a monster. It really shouldn't be there. And also, it eats very fast. Otherwise, it could not have, grown so massive in the first billion years. So, the black hole eats like a beast, if I may put it that way. And we believe that every galaxy in its early stages did this, but in most cases, we can't actually see the surrounding galaxy. In this case, we're lucky enough that we see the remainder of the train wreck. And so I should point out that Professor Gary Williger and Lutz Habersettel have also found many of these quasars at redshift 2 and 3, so they happen fairly often. But back in the early days, in the first billion years, they were not so common. They're hard to find. So let me now get to the second part of the talk about the Webb telescope, basically the last real technical part, and then a few more slides in the first slide. I'll go through this a little more quickly, so I'll skip a few slides for the sake of time. This is not James Webb, the second NASA administrator. This is actually somebody who wrote this book, Something to Die For. And yes, we're trying to recruit grad students to work on this project 4 years from now, but it's not really worth, but it's work hard for the project if you like. This was actually the senator, senator in Virginia, Mr. Jim Webb, who once upon a time was a good fiction writer before he became senator. Here's not the real Webb telescope. Of course, we don't expose it to the elements. That's a traveling mock-up that Northrop Grumman, the prime contractor, uses to show you how big it is. It isn't true size. It is a human being. And you see it's quite prominently placed in front of Congress here, with a few other things on display here, like some military outfits. So let's see, and that's a number of years ago. Here's the real thing. Of course, it's still an engineering model. It's not the real thing. We haven't completed building yet, but it's 6.5 meters across, which is about the size of this platform here up front, and a full 25 square meter area in collecting area, which is much, much bigger than Hubble. It will also work at longer wavelengths, roughly from the visual, what your eye can see, 0.6 microns to 28 microns, which is in the mid-infrared. And to work well at those longer wavelengths, it needs to be very dark, very cold, so you need to get it down to 40 kelvins. And if you do that, you can see this depth for the astronomers in the audience, which is roughly the faintness of one firefly from the moon. Of course, with the moon not there. So as we saw in the movie in the beginning, this thing will go up, folded up like a giant bat with the wings on the side, inside the launch fairing of the Ariane 5, which in a couple of minutes will make it across the Atlantic and will dump its first and second stage. And then the telescope itself will make it around an orbit of the Earth, and then the last stage will bring it on away past the orbit from the moon. It goes up not from Cape Canaveral, but from Kourou, because the Europeans are also heavily involved. So it's a French launch vehicle, well, European launch vehicle, I should say, the Ariane that goes up from French Guiana. So if this is the Earth, that circle is the moon's orbit. We go to this point over here. It's called the second Lagrangia point. It goes with the Earth around the sun every 365 days. The sun will be there about 100 times further away than the moon in this picture. And it goes around the sun with the Earth. And it takes about 2 months to get there from the Earth. And during those 2 months, you did a very slow deployment that you saw in 24 seconds in the opening movie. We'll get done here. Once it gets there, it describes some kind of what we call spirograph or Lissajous figure, where it has a vertical amplitude that's just about as big as the distance from here to the Earth. So it describes an enormous volume, and It floats freely there in space with a couple of other satellites like Herschel and Planck and a few others, WMAP. There's almost no chance of collision. Low Earth orbit 300 nautical miles away from the Earth's surface, you have tens of thousands of satellites and debris pieces. We don't have that in L2. And from there it's so dark, and the sun is always behind your sun shield, if you do it right, that you can observe more than 70% of the time. So you look at any part of the sky that's visible as you go around the sun, take your picture. I don't have to say much about this, because you saw already that in the movie. Just to say that all 18 mirrors have been made, and we're now in the process of, they're all within spec, and we're now in the process of testing the whole system for the next 3 years, both at NASA Goddard Space Flight Center in Maryland, Northrop, the prime contractor in California, and also Johnson in Houston. So each of these mirrors, each of these 18 mirrors is a little less in diameter than this table, about 1.3 meters, made out of beryllium. Very lightweight, very stiff material. It's like aluminum, it looks like aluminum. It's also highly poisonous, you can't breathe it. It gives you, like asbestos, that will give you lung problems. So you have to very carefully make it. And this mirror is figured and has this hexagonal honeycomb structure in the back. They put these 3 redundant sets of fingers underneath it. We call them hexapods. And each of these hexapods has 7 degrees of freedom, meaning you can tilt it and tip it, move it, push it and pull, translate and rotate. You can move it in every which direction, so that each one of these mirrors can be pushed in exactly the right position and shape with these redundant mechanisms. And it all has to work in 40 Kelvin. So each one of these hexapods has these redundant mechanisms that get tested many times. So here's all the parts of the telescope that are now